Hi, my name is Manish Gupta, and in this video, I'm going to talk about response sampling in large language models. This is based on a paper which got awarded the Best Paper Award at ACL 2025. So let's get started. The central question that this paper asks is this: are LLMs biased towards making descriptive choices or prescriptive choices? Which of them, right? So, and let me sort of help elaborate on this question using an example. So consider an example. If you ask a large language model, hey, how many hours per day should I watch TV? Right. So that's an interesting question to ask. And there are two ways in which the large language models could answer this question. They could probably have learned some sort of a statistical knowledge while pre-training or instruction tuning that, hey, possibly 8.6 hours or rather 8.6 hours per week, or maybe, some 10 hours per week is basically what people watch number of hours per week or per day. There is some number that the LLM might have learned on average that people watch, right? So that's called the statistical average or the statistical norm, also called as the descriptive statistic, right? However, there could also be an ideal that that the LLM may have in mind. So, for example, maybe it has read somewhere that ideally people should not watch more than, let's say, 30 minutes per day of TV, right? Or something like that. So now, when you ask a large language model, hey, how many hours per day should I watch TV? Does it really depend on an established average across whatever it has seen in its pre-training data, or does it really bias more towards the prescriptive or the ideal choice in that senses, right? So there is a descriptive, statistical descriptive average, and there's a prescriptive average, which is basically more like ideal in that senses, right? So what does the LLM choose? Where is it biased more when it basically comes up with a response, right? So to answer this question, basically the authors studied various models, instruction-tuned variants of GPT-4, GPT-3.5 Turbo, Claude, Mistral, and pre-trained and instruction-tuned variants of Llama 2 and Llama 3, right? So several models they studied, and whatever I will describe in this video is based on GPT-4, but the trends are similar across other models as well. So to understand this, let me actually talk about another concept, another question of this kind. How many sugary drinks should I consume weekly, right? And let's say the pre-training knowledge tells the LLM that, hey, 8.6 is the average that people consume. Now, obviously, from the descriptive statistics from the pre-training corpus, you could possibly get a distribution over, how many sugary drinks do people consume weekly. So where the mean could be 8.6, and then there could be a standard deviation like that, right? So that's basically the descriptive statistics, right? However, ideal could be zero. I mean, ideally, LLM might believe that, hey, ideal person should not consume any sugary drinks per week. Okay. So what is observed interestingly in an LLM is that LLMs for these concepts, so sugary drinks consumption is like a concept C, right? For such concepts, LLMs basically make a choice. So rather than following the statistical distribution, they also have this ideal in mind, and they actually get they still follow a Gaussian distribution when they come up with responses, right? When they make a choice, when they basically, if you ask an LLM, hey, how many sugary drinks should I consume per week? It'll come up with a response, and the response is not deterministic. It's going to be still distribution, but this distribution is going to be biased towards the ideal. It's not completely the statistically observed distribution. So it's basically not going to, if you basically ask it 100 times, the average is not going to be 8.6. It's actually going to be somewhere between 8.6 and 0, right? So as you see, the LLM sample distribution, when you sample an LLM and ask it multiple times, it's going to be biased towards the ideal, the blue guy, rather than just being very, very similar to the green one, okay? So the statistical norm here is denoted using A of C, which is basically 8.6. This is based on the descriptive statistics, right? While the prescriptive norm, prescription is basically ideal typically, right? So prescriptive norm is like ideal, which is basically 0 in this case. You want to prescribe that, hey, don't take any sugary drinks, right? Ideally. So that's that. And the idea is that there is a deviation when you basically study these LLMs across several of these concepts. And I'll talk more about those the experiments that these guys did. But when you look at these concepts, specifically sugary drinks consumption, you observe that the LLMs are biased with the sample mean of 4.5. So there is a bias alpha. Alpha is basically 8.6 minus 4.5. There is a shift in the distribution that happens because LLM has a notion of ideal. Now, this is very interesting. What is the notion of ideal? Now, for this concept, LLM believes that humans should consume zero sugary drinks per week. But ideal really is not golden, right? Depending on the culture, the ideal might be very different across different kinds of concepts. And therefore, this is worrisome because LLMs have a notion of ideal that could be different from the notion of ideal that you or I have in mind, right? So that's basically that. Now, to study this in more detail and more rigorously, these authors essentially studied with synthetically generated concepts. So what they did was to basically come up with a concept like a fictional concept like glubbing hours, right? So these concepts that I talked about on the left side, sugary drinks or watching TV, are not synthetic concepts, but they come up with a very, very synthetic concept so as to study what happens to LLMs when they do not have anything impacted by their pre-training knowledge. That is why they study with synthetic concepts. So they basically said, hey, let me consider several of these, 100 of such synthetic concepts like glubbing hours, right? Glubbing is not a real term, right? Basically, it's just some glubbing concepts, right? And then what they did was to prompt the LLM like this. There's a hobby called glubbing. Here are the glubbing hours of people. So they basically gave exactly 100 such glubbing hours of people. So thereby telling in the prompt itself that, hey, when you want to come up with a descriptive statistic, here is basically what people do, right? And you can basically compute the mean over them, and that should give you your a statistical descriptive distribution in that sense. So 43, 35, 63. You take the average, you take the standard deviation, and that gives you the statistically observed distribution, and that basically supplied as part of prompt itself. Okay, but you also tell it a notion of ideal. So, and the way you tell the notion of ideal is by basically also associating a grade with it. So basically saying, hey, I'm going to give a grade of C to this guy, C minus to 35, B plus to 63, and so on. So the idea is that maybe glubbing is a positive activity. So maybe you want to say that, hey, I'm going to give like A plus score to if somebody does 100 hours of glubbing in the day, right? Or in the week, whatever it is, right? You can't do 100 hours in a day. Yeah, I mean, so, 100 hours per week. Yeah, I mean, then you give an A plus. And I'm going to give like say D minus if basically people just do like 5 hours per week in that sense. Okay. So the idea is that in the prompt itself, you describe the task or the concept to the LLM. You also describe what is the distribution of the observed data, so statistical distribution, and you also give it a notion of ideal because you basically give it a grade for each of those values that you describe, in this prompt. And then you give a sampling prompt. You basically tell it, hey, now that you know about all of this, based on this, pick a sample number of glubbing hours for me. Tell me, how many glubbing hours should I be doing? Okay. So they may experiment by sampling these 100 numbers that you see here with a mean of 45 and a standard deviation of 15. That's how the synthetic data is generated for the prompt. And they basically do several such prompts with several variations of sample prompts and so on and so forth, right? So, and what you observe is the following. So when you ask it, obviously you can sample several times from the model, and then based on that, come up with a sampling distribution the model provides. So there's an actual distribution, which is basically the statistical distribution that you basically provided, which has a mean of 45 and a standard deviation of 15. But then you can also observe, hey, when the LLM is going to output samples, maybe when you basically ask it 100 times with different temperatures and so on, right, settings and so on, what is the sampling distribution? So what is the mean of the sampling distribution, right? So, and they experiment with multiple sampling prompts. But then, when you sample, what could happen is that there is a possibility that the LLM did not really understand the task, and the LLM could not really capture the mean from the data itself. Okay. So therefore, they also ask the LLM, hey, tell me what is the mean that of the statistical data that I supplied to you as part of the prompt itself. Okay. So the LLM agrees. So, you see, in most of the cases, LLM basically so there are these 3 rows, and I'll talk about the 3 rows. But the idea is that they observe that the LLM has understood the task. They observe that the LLM has understood the actual mean from this distribution that was provided in the prompt. So that is a possibility that is rejected in the sense that, LLM does understand the distribution very well. Okay. Now, what they do is that when they associate these grades, they basically associate grades in 3 ways. So they basically have a notion of ideal. So, you can basically say that maybe, higher glubbing hours is a good thing. And that's basically the CV positive that you see, right? So basically higher clubbing hours are going to be considered positive, right? So you will give like, so 100, you will basically give a grade of A plus, maybe 90, you'll give a grade of A, then 80, you'll give a grade of A minus, and so on, right? So that is how you give the grades. Or you could do the other way around. So you could basically consider lower grading, lower clubbing hours are positive. So which is basically this guy. Basically maybe you give like, 100 clubbing hours, you get a D minus, but 5 clubbing hours, you give a A plus, and so on. Okay. Or you could basically, you could have this control thing where you basically say that, hey, since mean is 45, let me consider, A plus as 45. But then on both the sides of this 45, maybe 40 and 50, both of them are A. And then, and so on. So 35 and 55 are both A minus, and so on. Okay. So what do you observe? So you observe that that when you ask the LLM, hey, tell me what is the actual distribution, statistical distribution that you observe from the data, the LLM does understand that. You see, these numbers are very close to 45. So the LLM has understood that this data that was provided to it was sampled from a Gaussian with mean 45. Okay, so that's good. Okay. However, when you ask it to sample and generate, and prescribe, pick a sample number of clubbing hours, basically you see, uh, when you give the ideal as positive, basically it gives you much higher than 45. When you give the ideal as negative, it comes up with a number much lower than 45. And when you basically give, the grades which are centered on 45, highest grade is centered on 45, you basically get the sample distribution close to 45. This clearly shows that the LLM tries to not just depend on descriptive statistics, but tries to, bias itself towards ideal. Okay, bias itself towards ideal. So it's an interesting thing because humans also do the same thing. I mean, the conclusion from this slide, the takeaway is that LLMs deviate from the statistical norm towards a prescriptive component of what is ideal, right? Consistently across concepts. And they basically try to do these experiments across several concepts, right? Just like humans, they basically try to be idealish in nature, okay? Now, this may or may not be desired in many, many situations. In many situations, people may want to just get a statistical estimate rather than getting the ideal. But this is what happens with LLMs as they have observed in this particular synthetic experiment. Okay. So what they also try to do is to vary this mean. So when generating the synthetic data, they also try to vary the mean. They said, why just keep mean as 45? Let me vary the mean. So the mean was varied, across, across experiments. But for this particular experiment that you see here, what they did was to keep the mean fixed, for example. So keep the mean fixed as 45. But what they did was to vary the ideal. So in this experiment that you see in this chart, they varied the ideal. So they varied the ideal saying that, hey, the ideal is going to, the A plus grade is going to vary from 25 to 75. And as you can observe, so the S of C is the sample distribution. As you can see that the mean, basically, mean is on the y-axis, right? The red curve, basically, that you see, okay? And ideal is on the x-axis. As you can observe, they are highly correlated, correlation of 0.94. Basically saying, if you vary the ideal, the sampling distribution basically gets biased towards that ideal with very high correlation. So this is a very, very confident estimate. Therefore, therefore the confidence in this statement that LLMs deviate from statistical norm towards ideal is basically with a very high confidence, very high confidence. Okay. Now, this was about synthetic data, but these studies have been done for humans as well in the past, right? So people have tried to do with humans, give them a notion of what should be the average. What do you think? What is the average number of hours that a person watches a TV? And then humans have been also asked, what is the ideal number of hours you think that people should watch a TV? And then humans have also been asked, what is the number of hours that you tell that I should watch TV, right? So they tried to do the same experiment with the LLMs with real concepts now, not synthetic concepts. So they took like 500 real concepts across 10 domains and asked 15 different LLMs these kinds of questions, right? The concepts are basically of these kind. 10 different domains, 3 of them I'm showing here, like percentage of students in a high school to drop out, right? What do you think is average such percentage of students? What is the ideal percentage of students? Now, ideal percentage of students in a school to drop out, most humans would just say 0. I don't want any students to drop out, right? But some humans are, well, whatever, right? So ideally, you would want it to be 0, right? What is the number of percentage of students in a high school to drop out? Just give me some number. Now, that's the kind of questions that you ask an LLM and you ask a human as well. And there are, you can read through these questions. There are 500 such questions that were asked to LLMs. Okay. Now, obviously, for these kinds of things, there is no publicly known descriptive statistic. Now, who knows on average how many, what is the percentage of students in a high school that drop out? And what is the Gaussian that is followed, right? So what is the standard deviation of this Gaussian? Nobody knows, right? But you can ask an LLM, and the LLM can actually tell what it believes is the average, statistical average, okay? So you could also ask the LLM, hey, what is the ideal value, okay? And then basically, and the way you do this is using these prompts. What is the average number of hours of TV a person watches in a day? What is the ideal number you think the person should watch TV in a day, right? And then you tell it, hey, now can you sample and just tell me the number of hours of TV a person watches in a day? Okay. So you see, you're asking the LLM itself for the average. So in the synthetic experiment on the previous slide, you didn't need to ask the LLM for an app. Well, you still did ask the LLM for the average because you just wanted to confirm if the LLM has understood based on the input data that you provided, right? Here you don't provide any input data. Here you just depend on its pre-trained knowledge, right? In that senses, okay, or RLHF knowledge in that sense, and so on, okay. So, but you can ask and identify what it believes is the average, what it believes is the ideal, and then what is the sampling distribution that it provides. Okay. So, and then what you do is to check the number of concepts out of these 500 for which the sample falls on the ideal side of the average. Remember, from the previous experiment, we found that LLMs, do not give you the sampling distribution which is matching the statistical average distribution. It gives you, a sampling distribution which is more biased towards the ideal. So to verify the same thing with real concepts, they basically try to figure out of 500 how many concepts the samples basically fall on the ideal side of the average. Okay, and what they found is this thing across different 15 different LLMs. As you see. So for example, with GPT-4, they found that 68% of the times, basically the number of concepts, 68% of the concepts, basically the sample falls on the ideal side of the average. Okay, so for 68% of these 500 concepts. Okay, and now different LLMs have different fractions with which they prefer to be biased towards the ideal, right? But GPT-4 is biased 68% of times. Okay. In fact, there are these two interesting conclusions that the influence of prescriptive norms or the influence of the ideal gets larger as the model size increases. So if you look at smaller models like Llama 2 7 billion, it's just biased 54% of the times towards the ideal. But if you look at the large model like GPT-4, it's biased significantly large number of times. Okay. Also, prescriptive norm or the ideal seems to stem from pre-training rather than RLHF knowledge, though RLHF exacerbates it even more. So, here are these RLHF variants like instruct model and the chat models. As you can observe, the pre-training knowledge itself made the bias to 62%. Now, obviously, it is also observed that with RLHF variant, it increases even further. But even the pre-trained models themselves have this notion of preferring the ideal when you ask it to recommend something. Okay, so here are some examples. Like, for example, how many minutes do you think we should wait on phone for customer service to respond? Okay, and the statistical average that the LLMs reported, GPT-4 reported, is 11.3 minutes. Okay, but then if you ask it, hey, what is the ideal? It basically tells 3.1 minutes. Well, for whatever reasons, right? But then if you basically ask it for a sample, the sample is much more closer to the ideal compared to the average, right? So basically here, the alpha here, where alpha basically denotes the bias that the large language model has towards choosing things closer to the ideal rather than what is the statistically observed average. That alpha is so large, 7.9, right? So that's that. And by the way, this is not based on one sampling. Remember, this is actually based on several statistically significant samples that they did. Okay, so that's an interesting thing. Now, this is interesting to know that LLMs choose to provide a sampling distribution which is different from a statistical distribution and more biased towards ideal, but it has repercussions on real things. Okay, and let me talk about those repercussions that they actually present in this paper. So but before that, let me just talk about how these LLM choices correlate with humans. If you ask a human, what does the human respond typically? Okay, so these experiments were actually already performed on humans in the past. Okay, so both with the synthetic concepts and with the real world concepts. Okay, so and what is observed is that for a new concept with prescriptive, that is ideal, and descriptive statistics, both humans and LLMs capture these prescriptive and descriptive statistics and use them to sample the options. So basically, the idea is that both humans and LLMs are biased towards the ideal when you ask them for a response, right? In that sense. Interestingly, both undersample negative value scenarios, both of them have a tendency to not sample much from the ideal, but oversample positive ones, oversample more closer to the ideal, right? So both humans and LLMs understand what is ideal and what are the standard distributions, standard statistical distributions, but both of them tend to undersample from the negative values far away from the ideal, and both of them tend to oversample from the positive ones, as we have seen so far. Okay. However, the interesting aspect is this: the notion of ideal differs between humans and LLMs. Okay. In fact, LLMs are more morally absolute in nature. So for example, consider this concept: number of sugary drinks per week. Okay, if you ask a human, hey, what do you think is the average number of sugary drinks per week that people consume? So humans basically say that the average is 9.17. Okay, but if you ask people, yeah, what do you think is the ideal number of sugary drinks per week that people should take, that humans should consume? Humans basically say that the ideal is 2.41, but LLM says sugary drinks are bad for health. Ideal should be 0. Okay, so LLMs are too strict. They are too morally absolute in nature. Okay, while humans are sort of more flexible. Okay, so this is a very interesting aspect because LLMs believe in moral absolutism. And again, this study was basically the human-based study is obviously more West focused here. Now, obviously, these kinds of concepts could differ across geographies, across cultures. So what is ideal? A number of sugary drinks per week for Indians may be very different from number of sugary drinks per week for Americans. So that's a different case altogether anyway. But the idea is that LLMs have a notion of number of sugary drinks per week that is ideal for them. Okay. And LLMs basically say it's basically 0. Okay. And that's not just for this concept. That's actually true across several other concepts, that LLMs have a stricter notion of ideal compared to humans in that sense. Okay. Now, let me basically talk about this case study that they provide in this paper, where this has a very important bearing. Okay. So the LLMs were basically asked, so they were given 4 symptoms of a patient. So they basically, they were told, hey, these are the 4 symptoms that I see in this patient. Now tell me, what should be the discharge time for this patient in terms of number of weeks? Okay, should it be 2 weeks, should it be 4 weeks, and so on. Okay, now you see, and these 4 symptoms, they basically did like 35 batches of these 4 symptoms. So these LLMs were basically given these 4 symptoms, and you do this 35 times. So you have like 35 different combinations of 4 symptoms. For every combination of 4 symptoms, you repeat the experiment 100 times so as to basically get a good estimate of what the LLM will you say. Okay. So that's that. So 35 batches were provided of 4 symptoms each. What was observed, and LLM was basically asked to give the average, give the ideal, and give a sample. Okay, give the average, give the ideal, give a sample. So what does this mean? This basically means that the LLM was asked these 3 questions. Hey, given these 4 symptoms, tell me what is the average discharge time in terms of weeks. What is the ideal discharge time in terms of weeks? And then, tell me, what do you think should be the discharge time for this patient? Okay, that's that. So 30 on 35 times, the ideal was lower than average, as you would expect, right? Even if you would ask a human, what do you think would be the average discharge time for this guy? You would give some average discharge time. But then you ask, what should the ideal discharge time? Now you would say, yeah, I mean, ideally this guy should be discharged much faster. But I'm telling you that this would be the average discharge time because, in realistic scenarios, doctors are late, some infection may happen, this and that may happen, and so on. Practical scenarios, right? So that's that. So LLMs followed the same thing. 30 on 35 times, ideal discharge time was lower than average. However, interestingly, because of what we have studied so far, what we have observed so far, LLMs chose 26 of 35 times, they chose to sample in the sample distribution. Samples fall on the ideal side of average. What this means is that LLMs actually sampled a lower than statistical average value. Okay. Now, in this particular case study, this is not expected. A patient, when they ask a LLM, hey, tell me what would the average discharge time with these symptoms, the patient is really, really looking for the statistical average and not something that the LLM believes will be closer to the ideal. Okay. So it clearly has several implications in terms of clinical decision making, in terms of resource allocation, hospitals, in terms of potential risk to patient safety, right? So therefore, I mean, the crux of the story in this paper is a very interesting paper. It studies the belief that LLMs have in terms of distributions with respect to several concepts. And what they found is that LLMs don't always, in fact, LLMs don't really try to sample from the descriptive distribution. They have a knowledge of descriptive distribution across these concepts, but they don't sample from the descriptive distribution. They sample, they also have a knowledge of ideal, and they have their own notion of ideal. So they sample somewhere between the statistical average and the ideal. That's an interesting aspect, which is sometimes worrisome. Okay, so the exact notion of ideal is more strict in LLMs compared to humans, and some applications may desire just the statistical descriptive outcomes only, without any impact from ideal. But the control knob in these LLMs is not available, unfortunately. Right. So that's basically that. Now, obviously, this has several implications in terms of the way people use these LLMs. But that's basically future work that people have to deal with as part of responsible AI. Okay, that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.